Welcome to day 14 of Math 007. We're going to be solving word problems with systems of equations and systems of inequalities. These are similar problems to the word problems we did before, only this time instead of just using an equation with one variable, we're going to use two equations with two variables. Our first example is that Robert is 15 years older than Helen. The sum of their ages is 63, and we want to find their ages. Well, R is going to be Robert's age, and H is going to be Helen's. So we start off then with our system of equations is that R minus H is equal to 15. That's our first part of the problem here. And then R plus H is 63, which is the second part. I elected to do linear transformations to solve this. I added the first and second equations and plugged it in as a new second equation. That gave me 2R, and then minus H plus H dropped out. That's 0. And then 15 and 63 is 78, which was kind of a big number, so I elected to go ahead and divide this equation by 2 and plug that in for my new second equation. So we get R is equal to 39 when you divide 78 by 2. Okay, so now we want to get rid of the R in the first equation. Okay, so we'll take the second equation and subtract the first equation from it. That will give us, and plug that in for our new first equation. So R minus R is 0, that drops out. 0 minus the opposite of H is just H. So we end up with H on the left here, and then 39 minus 15 is 24. So that gives us then that Robert is 39 years old and Helen is 24. So if we go to check that then, the difference in their ages is 15. Well, 39 minus 24 does equal 15. The sum of their ages is 63. 39 plus 24 does equal 63. So that all checks out. So that tells us that Robert is 39 years old and Helen is 24. Now, if you have any questions on this, please send me a message during the regular class time on Canvas and let me know which of these examples that you're having a problem with, and we'll get to town on it. Our second example involves angles from geometry. Two angles are complementary. That means that the sum of their measures is 90 degrees. The measure of the larger angle is 10 degrees more than 4 times the measure of the smaller one. Find the measures of both angles. So A is going to be our larger angle and B is going to be the smaller one. So we have A plus B is equal to 90 from the fact that they're complementary angles. And then we have that A is equal to 4 times B plus 10. That's what this description here means. This time we'll use substitution because we already have this equation solved for one variable in terms of everything else. So if we plug in 4b plus 10 for A in the first equation, we get 4b plus 10 plus another b That's equal to 5b plus 10 when we combine our terms. That's going to be equal to 90 degrees. So we want to move the 10 over to the other side. We do that by subtracting 10 from both sides, since this was a positive 10. And we end up with 5b is equal to 80. Then we divide both sides by 5, and we get that b is equal to 16, since 80 is equal to 5 times 16. So our smaller angle is going to be 16. Let's take that then and plug it in for b over here, and we get that a is 4 times 16 plus 10. 4 times 16 is 64. 64 plus 10 is 74. If we check that up here, 74 plus 16 does equal to 90. And if we plug in 16 for b, multiply by, that's how we got a to begin with. So we know that's going to work. Okay, so the larger angle is 74 degrees and the smaller is 16 degrees. For those of you that actually look at these videos, let me know if it's more of a distraction for you to have all this worked out ahead of time. I got a little crazy when I was doing a little preparation. I meant to only just get it down to where I had the two equations I started with, and then the next thing I knew I'd already solved the first one, so I figured, well, we'll just do all of them like that. Okay. Example 3. College roommates John and David were driving home to the same town for the holidays. John drove 55 miles an hour, and David, who left an hour later, drove 60 miles per hour. How long will it take David to catch up with John? Okay, John's time is t, and David's time is s. So we're told by the fact that David left an hour later that t minus s here is equal to 1. There we go. And then we know that since both distances are equal, if we subtract one from the other, we're going to end up with 0. Or you could just start with 1 on the other side. 55t is the distance that John drove, and 60s is the distance that David drove. Okay. So I went ahead and used substitution. Add s to both sides in the first equation, and you get that t is equal to s plus 1. So let's plug that into the second equation. So we'll have 55 times s plus 1 minus 60s is equal to 0. If we distribute the 55 over the quantity s plus 1, we get 55s plus 55, and then the minus 60s is equal to 0. So we'll have 55, and then 55s minus 60s is minus 5s. So 55 minus 5s is 0. So and then take the minus 5s to the other side, and you get 55 is equal to 5s. Divide both sides by 5, and you end up with s is equal to 11, which is really all we need in this case. It's going to take 11 hours for David to catch up with John. And it turns out then that means, of course, that John has driven 12 hours, 11 plus 1. I suppose we could double check, and we'll have 55 times 12 minus 60 times 11 . 55 times 12 ends up being 660, and 11 times 60 is 660, and lo and behold, it does equal 0, just like we started it out with. Again, send me a Canvas message if you need help, and I'll get back to you. All right, the last example for word problems with systems of equations is a mixture type problem. Sherry is saving nickels and dimes in a coin purse that she's going to give to her daughter. The total value of the coins in the purse is 95 hundredths of a dollar, or 95 cents. The number of nickels is 2 less than 5 times the number of dimes. How many coins of each type are in the purse? Since we started out in terms of dollars, I went ahead and wrote this up. 0.05 times the number of nickels plus 0.10 times the number of dimes. That's equal to 95 cents, or 95 hundredths of a dollar. Not wanting to deal with the decimal points, I went ahead and multiplied through by 100, and that gives me 5n plus 10d is equal to 95, which, if you did this in terms of cents instead of dollars, that's what you would have started out to begin with. And then, of course, the second equation refers to the fact that the number of nickels is 5 times the number of dimes minus 2. That's that 2 less than 5 times the number of dimes. Again, you already have it, so set up for doing the substitution method, so we might as well go ahead and do that. 5 times the quantity 5d minus 2 plus 10d. If we distribute that 5 over the 5d minus 2, we get 25d minus 10 plus another 10d is 95. 10d, 25d and 10d is 35d minus 10, then is equal to 95. If we add 10 to both sides, we get 35d is equal to 105. If you divide both sides by 35, you end up with d is equal to 3, because 35 times 3 is equal to 105. So then we go back over here. N then is going to be equal to 5 times 3 minus 2, or 15 minus 2, or finally 13. So that means we have 13 nickels and 3 dimes. If we check that, 5 times 13 is 65, 10 times 3 is 30, 65 and 30 is equal to 95. So that's our mixture problem, redone in terms of, and you really had to do it with 2 equations and 2 variables, because in this case we didn't have the total number of coins to start with and then determine the number of nickels and dimes. This way we didn't need to know that there were 16 coins altogether. All right, now before we can talk about how to do word problems with systems of inequalities, we have to talk about how do we solve systems of inequalities. Well, remember that with the lines, or with systems of equations, what we did was plot 2 lines and find the point where they intersected, or in the case where they were coincident, then it was, the whole line. But we're looking at intersections of two lines. Inequalities, remember, aren't lines. They are parts of they're like areas of the parts of the plane. So we're looking where two parts of a plane intersect. Okay. So we plot the solution set for each inequality, and then we see where the shading for those has crosshatched, and that gives us then our solution set for the system of inequalities. So our only example, our only example of this from just strictly solving a system of inequalities is this one. We want to solve the system 2x plus y is greater than negative 6, and minus x plus 2y is greater than or equal to negative 4. Okay, for this first inequality, we plug in a 0 for y to get the x-intercept. That'll have us at 2x is equal to negative 6. Divide by 2, that means that x is negative 3. So our x-intercept is negative 3, 0. To get the y-intercept, we plug in 0 for x, so that'll have us at y is equal to negative 6. So 0, negative 6 is the y-intercept. Okay, it's a strict inequality here, so we're going to use a dashed line and hollow dots. Here at negative 3, 0 is our x-intercept, and 0, negative 6 is our y-intercept. And then this is the line that goes through there, a dashed line, because none of these points, they form a boundary, but they are not part of the solution set. So now we want to determine which side of this line is what we want, is the solution set for this inequality. So we look at our origin here, 0, 0. If we plug in 0 in both sides, this whole side drops out. That's actually a handy reason for using the origin here, because whatever you've got with x and y is just going to drop out. So 0 is greater than negative 6, that's a true statement. So we want everything on the same side as our origin here. So that's everything over here to the right-hand side of this dashed line, which, if I hadn't already drawn everything in twice now, might be easier to see. So that's the first inequality. Let's look at the second one. If we plug in 0 for y, we get minus x is negative 4. So x then is positive 4. So 4, 0 is our x-intercept, which is the point here. And we have a solid dot because this is an inclusive inequality. If we plug in 0 for x, we get 2y is equal to negative 4, so then y would be negative 2, which is our other point here. Again, solid because it's an inclusive. And then we use a solid straight line then for the edge. So which side of the below or above do we want for our solution set? Well, again, we look at the origin. This whole side will become 0. 0 is greater than or equal to negative 4. So we want everything above. So this 1/4 section here, not including the edge here on this line, not including this point of the intersection, because it's part of the second line or second edge, say, but not part of the first one. So we exclude this point. And then the other boundary does include these on this line. So this is the solution of our system. Now, just as a point of interest, I solved the equation that goes along with this. 2x plus y is equal to negative 6, and minus x plus 2y is equal to negative 4. I use linear transformation to do it. Multiplied the second equation by 2 and added it to the first and plugged it in for a new second equation. So 2 minus 2x is 0x. Y plus 4y is 5y. And then negative 6. Oh, wait a minute here. Dang. Okay. Negative 6 plus negative 8 is negative 14. For a second there, I thought I goofed up. All these nice squiggle lines aren't helping anything. Okay, so then we want to get rid of the y in the first equation. And so we'll subtract 5 times the first equation from the second equation and plug it in for a new first equation. So 0 minus negative 10x is negative 10x. 5y minus 5y is 0y, so there's no y up here, no y term. And then negative 14 minus 5 times negative 6, that's negative 14 plus 30, or 16. So if we divide through by negative 10 here, we get that x is negative 8/5. Actually 16 tenths, but that reduces down into lowest terms to negative 8/5. And then y is negative 14/5. That's this point here. Okay. Now you'll probably have one like that on your assignment, in classwork assignment this time. So if you have questions on that, I'll answer them between 6:30 and 8 tonight, because you'll be watching this on Thursday. It's Wednesday right now. Okay. And then lastly, and this is actually a nicer way of doing it, on the test you'll be doing something like this. Okay, so for our word problem involving systems of inequalities, we have that Mark is increasing his exercise routine, which apparently is everything but walking and running, by running and walking at least 4 miles each day. His goal is to burn a minimum of 1,500 calories from the exercise. If walking burns 270 calories a mile and running burns 650 calories per mile, could he meet his goal by walking 3 miles and running 1, or by walking 2 miles and running 2 miles? Our system of inequalities then, if we let W is the number of miles that he walks and R is the number of miles that he runs, the sum of those has to be less than greater than or equal to 4, because he said a minimum, or at least 4 miles a day. He may have to do more. And then 270 times his walking miles plus 650 times his running miles, that total has to be greater than or equal to 1,500. All right, now rather than solving all of this and whatnot, all you have to do to check each of these cases is to just plug 3 for W, and in the first case, 3 miles for walking and 1 mile for running. So 3 plus 1 does equal 4, so the first inequality is met. However, when we plug in 3 for W and 1 for R, 3 times 270 is 810. 1 times 650 is 650. Add those together, you get 1,460, which is less than 1,500. So it does not satisfy the second inequality, and so he cannot do this new routine and meet all the requirements by doing 3 miles of walking and 1 mile of running. How about 2 miles each then? Well, again, 2 plus 2 is 4. So that one checks. If we plug in 2 for W and 2 for R, we get 270 times 2 is 540. 650 times 2 is 1,300. We add those together, we get 1,840. And that, of course, does satisfy the condition. 1,840 is greater than or equal to 1,500. So this solution works. He probably could get by with walking a little more and running a little less, but he's just looking for easy solutions to that. Okay, that is all I had to present for the night tonight. Good luck with the in-class work assignment, and don't be afraid to, if you can, call me between 6:30 and 8, and if you have any questions on this presentation. Okay, and that is the end of this.